The internal relay instruction here is an instruction which not control any output devices. So it's used to give you some like virtual output. Okay, so we can use it within the program of the PLC program, then to get or to check the output of a series of input instructions. So as you can see here, the advantage of using internal output is that there are some situation we need output or we need to know the output of several or of a connection of input instruction, but we don't want to energize any output device like any actuators. Okay, so the program will give you like output which is in term of bits. So it will be, for example, it will give you the output is 1, the output is 0, but this output will not be used to energize any physical device or any physical actuator for the circuit. We can find it here, or the representation or the bits of the internal relay will can be found in the binary table here. And as you can see here for the B3 1, this is the internal relay coil for P3 slot number 1 and terminal number 3. So here we have terminal number 3, slot number 1, and uh, the status of this bit is 0 actually. So for example, we have some instructions. These instructions are true. So the state, and then we use this internal relay. This internal relay status will become 1. So for SLC 500 controller, use bit 5 B3. So we can find B3, B3 1, B3 2, B3 3, B3 4, and so on. As you can see here, B3 0, B3 1, 2, 3, 4, and 4, 5 in the bit files. So this internal relay, each internal relay consists from, for example, here 16 digit or 2 words, and each each bit here represent one, one terminal or one bit can be used to be for the discrete case. When we use or we want to represent a discrete input or discrete output, it will, discrete output, so it gives you just either 0 or 1. So for example, when we want to define this location or this place of the bit, can be like file p3 word number 1 and bit number 3, because we have word number 1 from 0 to 7 and word number 2 from 8 to 15, since our each one represented by 2 words and each word is equal to 8 bits. Okay, so the address for this bit here will be B3 slot 1. Here when there is no real slot, but here the number 1 represent the slot inside the internal relay and or the file, and the 3 here represent the bit number. So usually the internal relay used for program that requires more series contacts. As we mentioned before in the previous video, we said there are some limitations for PLC. So the number, as we see before, can go back. So here, when we say there is like a limitation in the number of the series instructions and vertical instruction here in parallel or in series, horizontal and vertical. So if we have such limitation in the number of instruction, we can use the internal relay in order to make logic continuity from one line or from one branch to another branch. As you can see here, so for example, here we have the limitation of this PLC, only you can use 7 instructions. But in the process that we want to control, we have 12 instructions. So how we can make a series of instruction in or this instruction connected in series, the 12 instruction in series, without and overcome the limitation of this PLC. So the PLC cannot use more than 7, only allowed to use 7, for example, this type of PLC. So in order to use the 12, in order to energize the output device here, which is the discrete output, we can use the internal relay. So this internal relay coil will be placed in the first rank, and the output of this internal relay or the contact of this internal relay will be used in the second rank in order to create a continuity of or logic continuity of the instruction. So for example here, the instruction 1, 2, 3, 4, 5, 6, 7 are true. If these instructions are true, they will energize the internal relay. There is no real device. This is not real device. It's not a physical device. It's internal relay inside the PLC software. So this internal relay will be energized. Okay. If this internal relay will be energized, it has contacts, and one of its contact here is one B313 will be used in the second rank. So this will be also true. If this one is true, then we continue to instruction 8, instruction 9, 10, 12, 11. If all are true, then the output will be in. Okay, so we can see here we use the 12 instruction in order to make a decision of energizing the output device. This is the physical output device actually. Output device is here. That one is a virtual, is internal relay, and it's just like virtual output. Okay, so relay give you or when energized, make this internal relay contact energized or true. Then we check the status of other instruction. If all true, then this our output will be energized. Okay, so by using this internal relay, we overcome the problem of limitation of the number of series contact. Okay, this is how to simulate this situation here. So we have 7 instructions from 0 to 6. So it's 7 instructions. When the 7 are true, this relay or internal relay is energized and its contact is also energized. Then when the other instruction are true, the output will be energized. If one of them is off or false, this relay will be uh, de-energized and its contact will be false and the output will be de-energized also. Okay, and this table actually show you the status of the bit for our for the internal relay that we use, and here we use the relay which is B313. So you can see here B3, this is B31, and the bit number 3 is here. This bit number 3. At this point, 3 is equal to 1 because it's now energized. You can see here, this is 1, and thus our system is energized. Then we talk about the programming, examine if closed and examine if open instruction, and when we can use examine if closed and when we can use examine if open. Okay, so previously we already talked about these two type of instruction with in addition to the output in energized output instruction or relay. Now we just highlight when we can use examine if open and when we can use examine if closed. So actually the situation here, the selection of the type of instruction not depends on the status of the input here, not depends on the status of the input device or physical or hardware circuit. It only depends on the answer of the question when you want your output to be energized. The question that you want to ask or you have to ask before selection of examine of open or examine of close is when my output device or actuator should be energized. Okay, so if the condition I want this output device to be energized when both push bottom are closed, so just use examine if closed. If I want this output to be energized when push bottom is open, so use examine if open. Don't look at the situation at the status of this switch here. Okay, so now for example in this circuit we have push bottom is open here and the another push bottom is closed. So don't go to use examine if open, examine if closed to represent your circuit. No, I told you you have to ask when I want this pilot light to be energized. The answer is I want this pilot light to be energized when push bottom is closed, push bottom is closed. So just go to use examine if closed instruction. So we use examine if closed because we want the pilot light to be closed or to be energized when the both push bottom are closed. So now in this hardware circuit, this pilot in the normal situation is off. Why? because this one is open, this one is closed, so no electrical continuity from left to the right. Also the same here, no logic continuity from the left to the right, because push button 1, examine if closed, no, it is open, so this will be false, this will be true. So this will be de-energized because this one is false. Now if I press the push button 1, the electrical continuity is satisfied on this hardware circuit, so the pilot light will be switched on. The status of this push button will be changed of this instruction. So now examine if closed. Yes, push button is closed now after I press. If it's closed, that one is closed by default, so my light will be switched on or energized. So what matter is that contacts need to close to energize the output. So my focus will be more on when I want the output to be energized, not what is the status here. Don't look at this one. It is normally open. You both examine if open. No, it's normally open, but we use examine if closed. This one is normally closed. We use examine if closed also. The same. The second situation here we can how we simulate this situation here. Now one push button is normally open, but when I press it's become closed. In normally open case, our output is de-energized, but when we press this push button, this one become true, so the output become energized. Again, this de-energized now. When I press number 2, nothing, but when I press number 1, both become true, so this become energized, and the status of this one become 1. So you can see here the input 1 in the normal condition is 1. Why? Because examine if closed. Yes, it is closed. But the input 0 in the normal condition is 0, because in the normal condition the input 0 is open, it's not closed. Next, the examine if open situation instruction. Here the examine if open instruction, when I need to use it, I use it if I want my output to be energized when the input is open. For example, in this situation here or this scenario, we want the relay or the pilot light to be switched on if this push button is open. It's like the, if you can say, it's like the emergency push button. So in the normal case, our system is running, even this push button is open. But when emergency situation is there, someone will press the push button. When you press the push button, that means you are shut down your system. So the pilot will be off. Okay, so when we need to use the examine if open, if we want our output to energize if the input is open. So here we use examine if open. Yes, it is open, so this is true, so our output will be energized. So in the normal case, examine if open, yes, this control relay will be energized, this contact will be energized, this output will be switched on. This is how to simulate. If I press, it will be, you see here, when you press, in the normal case, this one is true. Examine if open. Yes, it is open now. It's open, so the pilot light is on. If we press, this become false because it's examine if open. No, it is closed. If it's closed, so this become off or de-energized. This the table we already see before, and we say the difference between examine if open, examine if closed, examine if open, and the output energized. So this is examine if closed, this is examine if open, and this is the output energized. So as we can see here, the logic status or the logic state 0 or 1 indicate whether the instruction is true or false. So for the case of the examine if closed here, if it is false, it means logic 0. If it is true, it means logic 1. This is for examine if closed instruction. But for examine if open instruction, logic 0 will give you true, logic 1 will give you false. Why? Because examine if open, no, it is closed, so it will give you 0. If it's open, so it will give you false. Okay, so the output here will depends on the status. So when this output will be energized, only if the first instruction is true, the second instruction is true. Okay, if one of them is false, the output will be false, or will be de-energized. Okay, so for example here in this situation, false true give you false, true false give you false also, no true here. In order to get true or energized for the output here, you must have both input instruction are true, this true, or that true, that true. Okay, sometimes there is a time delay between the situation to convert from the true to false and from the false to true. Okay, so as we can see in this table here, the time aspect relates to the repeated scans, because we said when we have a ladder logic program, the scan will be repeated. It go from the left to the right, top to the bottom, then again it will be repeated again. So it's a continuous operation, it's not stop. Okay, so when the status of the instruction change from true to false, false to true, true to false, and so on, in this case you will have some situation will have delay. So you can achieve to either two false input, two true input, and so on. So in the first initial condition here, examine if close will be false. So examine if close, no, it is open, so it will be false. Examine if open, yes, it is open, it will be true. If you have the two, as we see here, this will be false, this will be true because it's open, so the output will be false in this case. Then if I make the switch close, for example, then the instruction will check, examine if close, yes, it's closed now, so it gave you true. But this one is not yet check the status of the input, so examine if open is still open, so it will give you also true, because the time delay between the two instruction will give you the situation that both examine if close or examine if open are true, so your output in this case will go for true. Then again scan at the time 3 here, examine if close is true, yes, it's closed. Examine if open, already now check and found it's open, so it's false. Then again the output will go to the false. Next round, the if I open the switch, now it will check, examine if closed, no, it's already open, so it's false. Examine if open, it still keep or latching with the previous stage status, which is no, it's closed, so it will give you also false. So you have false, so the output will remain false. This is how the sequence, since we are not talking about just one scan, we are talking about a repetition of scans. So it is a cycle, correct? When we talk about the program, we take it as a cycle. We say the first scan the input, then update the or check the program, then update the output, then do the communication check, and so on. Then repeat again, scan the input, check the program, update the output, and do the communication test. So in this case, since you have a cycle, so some of the status of the input or the output instruction here will give you, due to the time delay, will give you the status of the previous scan, not of the current scan. So this will take for current scan, this one will take for the previous scan. For that, it will give you the output is equal to 1. We are going to continue in the next video.